Hi, this is Mr. Yeager. I'm calling this sound part two. Really just going over two ideas fairly quickly. It's a introduction to basically what is resonance in terms of, again, a behavior of waves, in particular sounds in this case. But any type of wave can do this. But resonance, and then a very brief introduction to what's called standing waves. We're going to look at one situation, standing waves on what's called a fixed end. And again, it's going to be very qualitative, not much calculation, too much involved with it. So what I have to first talk about is what's called resonance here. Okay, resonance is again a form of simple harmonic motion, and the key here is it's this whole definition here. It is a small force that is applied at regular intervals. So it's a force that's basically oscillating, an oscillating force, something that you keep on doing over a regular time frame, and it will cause an increase in amplitude. An increase in amplitude. All right? So the classic example I can basically talk about here that we always use is the idea of pushing somebody on a swing. Okay, pushing on a swing. Okay. So the idea is if you have a little brother, a little sister, okay, or you just have a friend that you want to go push on a swing, all right. Yeah, I mean, it's something you can almost do without looking at it. If they keep going back and forth, obviously ignore the idea of friction and everything like that. Clearly, they might not come back exactly the same. But I mean, it's something that you keep on doing over and over again. You could sit here and be starting to talk to a friend and know exactly when they come back. Obviously, they'll come out. You'll see at the corner of your eye. But you can sit there and kind of just keep on pushing over a regular interval. And what happens is, if there was no friction, the person would keep on getting higher and higher because you're adding a little bit more energy. You're doing work on them, so you're giving them a greater amount of energy, more amplitude. Okay. Now, other examples out there. All right, the idea of we use tuning forks, you can actually transfer a vibration from one tuning fork to an identical tuning fork. Trampoline jumping, I use that as like a double bounce. If you know what a double bounce is, where somebody's bouncing on the trampoline and you come in and hit it right at the same time that they basically do, and you send them higher. But there's also a lot of very bad things that can happen. All right, this is actually how stadium balconies have collapsed or have been very much damaged. You're talking about concrete stadium balconies. All right, because you can have all these people all bouncing up and down, all excited about the game, and then basically if they match the frequency of that concrete, the idea is the atoms themselves all vibrate at a particular frequency. If you match it, you can make them you can make the whole concrete start moving. So there's been damage to bridges and damage to balconies and stages, all right, but also to bridges as well. All right. This is a classic example that's called a bridge collapse. I would recommend kind of highlighting that and taking a look at that. It's the example actually in all the textbooks, but it's kind of funny. It actually ends up not being true resonance because it was a constant wind. But it'll give you the idea of what I mean. Basically the idea that the bridge keeps on oscillating more and more and more and more until it actually completely collapses. And it's a real bridge. If you want to take a look at that. All right, this is something that we covered back in behavior of waves, kind of just talking about it again very briefly. Okay, we talked about when something hits a boundary, it's going to some of it will reflect, some part of it will transmit. That's kind of just a quick review of that. I'm not going to worry about that too much. This leads us to what are called standing waves, and this link is just a neat one showing you ocean standing waves. It's an area, I believe it's in Hawaii. I might be completely wrong though, where the waves, there's an area that they kind of dredge out between the ocean and I believe an intercoastal waterway, and it creates this, what's called a standing wave. And like people can sit there and surf on it in one spot for a really, really long time. But the idea of a standing wave, the official definition is it's the result of interference between an incident and reflected wave. So the incident wave comes in, you can see it's at a fixed point. That's going to reflect back inverted. When they interact, you're going to have destructive interference. The thing is, if you keep sending waves in, you might now have destructive and constructive interference occurring during this time. We call it a standing wave too because it looks like you don't actually see the wave move down and back along the string or the object. We can do this with a giant slinky. It just looks like there's particular sections of the wave that are bouncing back and forth, that are going from crest to trough, crest to trough. It's almost like the idea, if you think of like jump rope, where basically the rope is, when it's down by the feet, is a trough, then it's a crest, trough and crest. But it's more where if you whip it straight up and down. Now, nobody's going to do a jump rope that way. That wouldn't be very nice. But it looks like the wave itself isn't moving. So take a quick look at that. The wave, the energy of the wave is moving into the ocean and into the intercoastal waterway, reflecting back. So you have a little diagram down to your right. That is what I mean by a standing wave. Okay? You don't actually see the flow of the wave traveling down. All you see is basically one area, certain areas of the waves are bouncing back and forth, and certain areas are staying completely still. These are two important terms. This would be mainly one of the questions I would ask is, how many nodes do you see? How many antinodes do you see? So nodes are the areas where it remains stationary. Okay? So you can see I stopped it. You have a node, a node, a node, a node, a node. That's where it's staying completely still. All right? Antinodes are what are the parts that are moving between crest and trough. But we don't count both of them at the same time. Basically, we're saying that antinode is currently a trough, currently a crest, currently a trough, currently a crest. But, all right, if I let it start going, it immediately switches. All right, so the antinodes are where there's a huge displacement. You get the largest amplitude displacement. You can see on the left, the other way we draw out standing waves. This is showing you actually an incident wave coming in. I'll kind of draw over it again. The incident wave coming in, hitting a fixed boundary. It came in from below, so it's going to return above. So this is another way that they draw standing waves. All right. So again, the nodes are always on the equilibrium point. 1, 2, 3, 4, 5. The antinode is the crest and trough. Now, if we draw it this way, the one on the left here, I only need to count just all the crest. Or you can sit there and go 1, 2, 3, 4. But the idea for this wave, it has 5 nodes and 4 antinodes. So you will have to be able to identify nodes and antinodes. All right. That leads us to basically our final topic for sound, harmonics. All right. And so harmonics are waves that are multiples, that are whole number multiples of a fundamental. Okay. And we are only going to do what's called a fixed and standing wave, which means it's going to, basically I'm going to have 2 strict ends where it's like I tie a string off on either side, and I have to begin and end with a node. So there's always going to be the nodes on the ends of this situation, nodes at the boundaries. Now the thing is, this definition still doesn't make much sense. They are waves that are whole number multiples of a fundamental. What the heck is a fundamental? Well, the fundamental is the lowest frequency of sound that will resonate, that will create a standing wave based on the conditions that you have developed with the boundaries. All right? And again, we don't get into much detail. In AP physics, we do a lot more calculations with this. All right? So this is the lowest frequency of sound that will resonate, which means if you find it, it'll keep on starting actually to reinforce itself and get louder and louder and louder. Okay? We do a lab called the resonance lab, where basically you hold a tuning fork over a tube that has water in it, and based on where it is, all of a sudden you'll hear this louder whoa, 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 whoa sound. Like it'll be just nice and quiet, the sound of the tuning fork, and then it'll get very, very loud. That's the resonance occurring. It's reinforcing itself. All right? So what do I mean by that? If you know the fundamental, you now know all the different harmonics. Okay? You now know all the other harmonics. And this is not, let me change that, whole number multiples of fundamental frequency. Okay? So what that means is there's different fundamental frequencies based on what you're working with. Okay? This is how music is essentially made. A violin has a different fundamental lowest sound, lowest pitch. Frequency is pitch. It has a different lowest pitch than the bass violin, which obviously has even a lower, it should hopefully have a lower fundamental frequency. So there is not a set fundamental frequency. All you need to know is, if I give you the fundamental frequency, I can sit there and ask about any of the harmonics. And every single harmonic is a multiple of the fundamental. The fundamental is sometimes called the first harmonic, if you want to think of it that way. All right? The fundamental is known as the first harmonic. We just call it the fundamental. We usually don't use the term first harmonic. But you can see the second harmonic would be 100 hertz. The third harmonic would be 150 hertz. The fourth harmonic would be what? 200 hertz. Always a multiple of the fundamental. Obviously, the mistake I see people make is they go, first, the fundamental is 50. Second harmonic, 100. And almost nobody misses that. Third harmonic, 200. No! Okay? You don't just sit there doubling. The second is 2 times the first. The third is 3 times the first. The fourth is 4 times the first. That's what the definition is saying. They are all whole number multiples of the fundamental. Now, I could obviously make you go backwards. I could sit there and go, the fourth harmonic has a frequency of 100 hertz. What is the fundamental? Well, if they're at the fourth harmonic, this is 4 times the fundamental, so 100 divided by 4, the fundamental frequency is 25 hertz. Okay? So that's kind of the main ways I'm going to be asking these questions back and forth with harmonics. Now, there's one more thing I will do. Oh, did I skip something here? All right. We already talked about pitch. Again, that means as the harmonic number is increasing, what's happening to pitch? It's getting higher. Increase the harmonic. Oop, now I'm messing up. If I increase the harmonic, the pitch should get higher. Increase harmonic, I increase frequency, which increases the pitch. Okay? So the fourth harmonic should be higher than the fundamental harmonic. Fundamental harmonic is the lowest for that particular instrument. All right? So the last thing I really need to show, this slide right here is just basically telling you this is how guitars basically are developed based on their different strings, where each string is developing a different harmonic frequency. Okay. This is a fun website if you want to go to it. It's like an interactive one where basically you play, you listen to the different harmonic frequencies. You actually press the button and play around with the different situations. Again, we're only doing what's called the fixed end situation. You'll see a couple other situations on there that I'm not worried about. So this is really kind of the last slide that I want to focus on. I don't care about any of this math stuff to the left. You do not need to worry about that at all. Okay? What I want you to see is this. What I'm showing you is the first 6 harmonic frequencies for a fixed situation, a fixed end situation. All right? So the top one right here, this is always what the fundamental frequency looks like. Always. Okay? Always, always, always. The second one here, this is what always the second harmonic looks like. Third, fourth, fifth, sixth. What I could ask you is I could say, how many nodes and antinodes on the fundamental frequency, on the fundamental wavelength? So let's count. 1, 2 nodes, 1 antinode. Okay, 1 antinode. Second harmonic. 1, 2, 3 nodes, 1, 2 antinodes. Okay, so I hope you've seen our trend already. On the fourth harmonic, 1, 2, 3, 4 nodes, 1, 2, 3 antinodes. So do you see a little pattern here? Okay? There's a couple different ways you can identify the harmonic number if I show you a picture. Obviously you can memorize it, but you can also look at nodes and antinodes. First off, with this situation, there is always one more node than antinode. Second, the antinode, the number of antinodes, is equal to the harmonic number in this situation. You can see fourth harmonic, 1, 2, 3, 4 antinodes. Fifth harmonic, 1, 2, 3, 4, 5 antinodes. It's something that you can see really quickly and just go, hey, I know which harmonic number it is. All right? I think that's all you really need to No, yep, that's basically it. All right, so pretty quick resonance. It's the increasing of the amplitude by applying a oscillating force that, like, think of the swings. And then with harmonics, main idea, it's a standing wave that's created by constructive and destructive interference. And then identifying the harmonic number based on nodes and antinodes. Also being able to calculate the different harmonic frequency. Always a whole number multiple of the fundamental frequency. All right, that's it. Thank you.